Okay, so last time we started doing internal loads, and we did this cantilever beam example where we wanted to calculate the internal loads at the midpoint, and we had a 1,000 Newton force at 45 degrees like that, and a torque of 5,000 Newton meters. That was half a meter, and that was half a meter. And then, okay, so we calculated the external loads, the reaction loads at the wall, and then we calculated the internal loads just using the vector sign convention, just saying this is a fixed joint, and so any couples we need to keep it in equilibrium are going to be there. Any forces we need to keep it in equilibrium are going to be there, and we did it all with the vector sign convention. But the problem with that is you get this indeterminacy if you work from the left, whether compared to whether you work from the right. You get equal and opposite things because of Newton's third law. So then I introduced this, our new sign convention, that said if you're working this way, so you're looking at kind of right end, you're working from the left to the right, then a positive tension is going to be that way, a positive shear force is going to be that way, positive bending moment is going to be that way, and a positive torsion is going to be that way. And if you're going the other way, these are all opposite. So positive tension would be like this. Bless you. Positive shear force would be like this. Positive bending moment is like that. And a positive torsion would be like that. And if you use this sign convention, whichever side you work from, you get the same things. So that's the benefit of this. And that's why we're using this wacky sign convention for what really is a pretty simple idea, that you just have a fixed joint where you make your internal cuts. It's a simple idea that gets sort of obscured by this funny sign convention we use. So I'm going to do this problem again with the new sign convention. I don't think I did that last time. Oh yeah, the time before. Yeah. So I'm going to do the above example again. Using this sign convention. The free body diagram of the whole thing, let's not calculate the external loads again. Even doing it once might have been too much. But this is where we want to calculate. Don't put internal details in your free body diagrams like I did. Don't ever do that. But I just did it to show that's where we're calculating the internal loads. So we have a force vector here of 707.1, 707.1. And a couple about this is our coordinate system, so a couple about the z-axis of 707.1 Newton meters. And then a torque that is a couple about the x-axis of 5,000 Newton meters. And then over here we have that external load, which is negative 707.1, negative 707.1, and then the torque of 5,000. I don't have units on anything else. So. Okay, so now what we're going to do, we know all these external loads, so we're going to isolate the piece that goes from the left endpoint to the dotted line. Yep.
How do we know the moment? 707.1?
We calculated all that from last time. So I'm just using,
Okay.
so first you isolate the whole thing and calculate the external loads. We already did that before, so I'm just going to use those again. You guys know how to do that stuff. So now we're going to make a cut. So our chosen body is going to be from the left endpoint to the dotted line. So a free body diagram looks like this. We're including all the stuff on the left endpoint. So that's 707.1, 707.1, and then a couple of 707.1, and then a torque in the positive x direction of 5,000. That's all the external loads on the left. What external loads do we have on the right of our member? So remember, our chosen body doesn't include any of this stuff or those forces on the end. So what loads do we have here? These are the internal loads. Yeah, tension, shear force, bending moment, and torque. Yep. And Newton's second law says, usually it's not too hard to do these without the table since everything's perpendicular, all the moment arms are perpendicular. Newton's second law says, so what are the forces? This 5,000, remember, isn't a force. The one with the double arrow, that's a torque. So our forces at the left end are just 707.1, 707.1. And then at the right, there's a tension that's in the direction shown. You can think of that as, I think a good way to think of these, if you ever get confused about the signs, is think of this being a force that's made up of a scalar t times a unit vector in that direction. So what's a unit vector in that direction? A unit vector is 1, 0. So t times 1, 0 gives you a force t0. Then that force v is a scalar v times a unit vector in that drawn direction. What's that unit vector? 0, negative 1, so times v, that's 0, negative v. Everything else is a couple, so that's all the forces. And from this you can see that T is equal to negative 707.1 newtons. V is equal to positive 707.1 newtons. And now let's do the rotational equation. I'm going to break it up into moments about z. So about z, we have the couple 707, whoops. So about the z-axis, And the about point, let's make that all the way at the left. You get the same thing no matter where the about point is, but this is what we're going to use in every single calculation of internal loads. Okay, so we have a couple of 707.1. Nothing else produces a moment. None of these other loads acting at the left end point produce a moment about the z-axis with the about point at the left end, because these forces act at our about point. That never produces a moment. And this torsion, this torque of 5,000, that's about the x-axis, so that doesn't show up here. So now go to the right side, and we have a couple of m. T is about the x-axis, so that doesn't show up. The tension T has its line of action going right through the about point, so that doesn't show up. But V does produce a moment. What's the moment arm for this force V? Yeah, it's x, but we did this at 0.5. Okay, so that moment arm is 0.5 in this case. So, yeah, so the way I like to think about this is it's 0.5 times V. And now think about, would it cause a positive or negative rotation around the about point? That's a pretty split. Yeah, I'm going to go with negative. So if this is a hinge here, this force would make it rotate clockwise. So that's negative. So minus 0.5 V, and that's everything, is equal to 0. Well, we already know what V is, so 707.1 plus m minus 0.5 times V is 353.5. And so m is equal to negative 353.5. Yes, thank you. And now the last one we have to do is the moment equation about the x-axis. And the about point we'll choose as the center of the cross-section. Question?
Center of cross section. That's so we're gonna, I guess we'll see what draw 3 body diagram.
I'm not going to draw any more, but if the, I'm just saying if, I'm just saying our about, the axis we're calculating, this about goes right through the center of the cross-section. That occasionally comes up. It wouldn't come up in this problem since those are both just couples. The about point doesn't matter. Okay, so about the x-axis, we have this couple is in the positive x direction. So that's 5,000. None of these other things produce moments about the x-axis except this torque T. And so those are equal to 0. and you get that the internal torque is equal to negative 5,000 Newton meters.
So if you didn't have that torque on the left endpoint, you wouldn't have to do that
Right.
third one,
That's right.
and you just leave it all here.
I guess you should say it's equal to 0. Okay, so now we've calculated the internal loads at that point. But where we're going with all this stuff is we want to use this as a tool for determining where fractures are going to start, where deformations, permanent deformations are going to start. And to do that, we want a way to represent the internal loads at every point along this length, not just at a single cross-section along this length. So what we would like is to have the tension, shear force, bending moment, and torsion as functions of x. As you travel from left to right along the beam. So what we're going to do is we're going to do the same thing that we just did. The calculation is exactly the same, but instead of choosing to make our cut 0.5 meter into the beam, we're going to take a cut at a general value x and do all of our calculations in terms of x. So it's the same approach. It's just that we're just going to make the distance from the left end to the cut x instead of 0.5. So that means that in the cases where x came up, and I think it only came up in one place, the only place it came up was when we were doing our moment equation about the z-axis. That 0.5 there was the moment arm of the shear force, right? And that's a 0.5 when we made our cut right at a 0.5 meter from the end. When we make that cut a general distance x from the end, that's going to be a minus Vx. That moment arm is going to depend on that variable x. But other than that, I mean, all the calculations are the same. It's just you have an x there instead of a number. So now we're going to cut at x where x is somewhere in the interval from 0 to 1. So let's draw this free body diagram. We still, over here, have the external loads of, what were those? Positives. Okay. And so all of these external loads are still the same. And now over here, we still represent the internal loads the same way. It's just that now those have the potential to be functions of x instead of just values. And we're still excluding some part of the beam. We just don't know how much. We're excluding 1 meter minus x of it. We're going to keep the origin and the about point right here. Okay, so Newton's second law says 707.1, 707.1 plus T0 plus 0 negative V is equal to zeros. None of that stuff depended on x, so we can get values for these. T is equal to negative 707.1. V is equal to positive 707.1. Now the moment equation about the z-axis. If you think of the origin as being at the left endpoint, then you can just think about that as a moment about the z-axis. Okay, so what moments are produced? Notice now that this distance, it was 0.5 before, but now it's x. Yep, we have that couple. And we have the couple, the internal couple, m. And then we have v times its moment arm. What's the moment arm for v? X. And is that going to produce a clockwise or counterclockwise rotation about the end? Clockwise, so minus vx. And then this is equal to 0. We have v, so this says 707.1 plus m minus 707.1x is equal to 0. And so solve for m, and you get 707.1x minus 707.1. And then the last one is the moment equation about the x-axis, all the way at the left end point. So what's producing moments about the x-axis? There's the positive 5,000. None of these other things produce moments about the x-axis, and then just the torque T. And so T is equal to negative 5,000 Newton meters. So if you're looking at this, in this example, there's actually some analysis you could do right now. If you think if you're concerned about this object breaking, where would you be most concerned? Well, what we see is that the tension and the shear force, those internal loads don't vary. They just are what they are. The torque doesn't vary, so we don't have, there's no difference as you move along. This one does vary, though, as you move along x. So where's the magnitude biggest for this? When x is equal to 0, that's when we have the biggest bending moment in absolute value. And so this tells you that you're most concerned about this breaking at the connection with the wall. Any questions about that?
So we can. Oh, yeah. X is 1 for X.
What?
The max.
Yes, that's right. Yep. So the x values only go, from the start of the beam to the end of the beam. All right. So in this one, these are all continuous functions, continuous smooth functions. Just a single function represents each one of these along the whole length. For 3 of the 4 variables, the function is just constant. For this one, you have a linear function. In general, that's not the case, though. In general, these are going to be piecewise functions. So in general, t of x, v of x, m of x, and torque of x are piecewise functions. And the candidates, or let's say the candidate x values for boundaries between subfunctions. You know what subfunctions are? Piecewise function? You can probably guess correctly. Yeah, so if your piecewise function has 5 separate functions, it's equal to your function's equal to 0 up until x equals 0.2, and then it's equal to x squared over 4 for x from 0.2 to x to 0.4, and then the next chunk. Each one of those chunks is a subfunction. And so between any 2 subfunctions, there's a boundary. And what we want to figure out is where the candidates are for the boundaries between these subfunctions, because that's going to affect where we make our cuts. So the candidate x values for boundaries between subfunctions there are sort of 4 categories. First are the beam endpoints. What? What? Yes. So point forces. I thought you were questioning whether the endpoints would possibly change the subfunction. I was willing to fight about that one. Point forces, point couples, and in this class we haven't talked about distributed loads yet, but also I will talk about those, and also where distributed loads change our candidates. Let's say where distributed load functions change. In the example above, we made one cut. In general, we're going to make one cut between every one of these candidates for boundaries. So we'll make one cut for every subfunction boundary candidate. That sounds complicated, but it's not. We'll make one, that's wrong. That's wrong. We'll make one cut between every pair of, in general, we'll make one cut between every pair of subfunction boundary candidates. Period.
Yeah, because if you have two acting on the same point, you don't count it as two.
That's right. Yeah, so all we're looking is for points that meet one of these, at least one of these four conditions. So, for example, if you had a beam where these 4 points, each one of those 4 points fit into these categories. So these are the boundary candidates. You would do a cut here, and a cut here. So if you have n points are boundary candidates, you need n minus 1 cuts. Okay, so let's do another example with a little more going on. So let's say this beam at the left end point is connected to the ground by a pin joint, and then at its midpoint it goes over a roller. And then at its right end point, at an angle of 30 degrees, there's a force of 1,000 newtons. And let's say that there's a torque on the end of 500 Newton meters. What are the internal loads? Well, the first thing we have to do is calculate the external loads.
How would the torque ever be a function of x?
You know, it will not be. But this thinking about it this way just lets us do all the calculations at once. That's all. Like sort of think about it the same way for all of them. It would have to be, is it possible that there could be some kind of distributed torque? Yeah, probably. So if there was any kind of distributed torque along the length, then it could depend on X. Like if you had a sleeve that was applying a torque over some finite area or finite length, then that would vary with X. But yeah, those won't come up very often, if ever. Okay, so step 1, calculate the external loads. So for that, we'll isolate the whole thing. We have this force of, what was that, 1,000? Torque of 500 there. And now we have to think about what these joints do. And this is basically, you know, we did this stuff a lot in statics. There's one difference now. We have to think about whether these joints apply a torque along the x-axis. So that's a new thing we have to think about. Okay, so let's first just think about it in 2D the way we're used to. What loads are going to be applied by this pin joint? Yeah, full force vector. It just prevents translation. So RA. And now think about whether that pin joint would prevent rotation about the x-axis. It would, you're right. So I'll write this as torque A. And that's all. It doesn't produce any moment about the z-axis. So we're done with that one. Any questions about that one?
Conventionally, do you try? Oh, I suppose the arrows don't really matter because it's not even.
Yeah, so for this one, since these aren't internal loads, I would just use the axis directions for the external loads. We only need to use those funny sign conventions for internal loads.
We're talking about the before, the towards or away from.
Oh, I'd say just the same way, like we didn't think about the force component directions for this. We just wrote it as a x and y. Do the same thing for this one. Just assume it's positive, and if it comes out negative, that's just as good. And now what happens at the roller? Yep, there's a force up, and then would that roller prevent? This one probably is a little more, you need to know a little more details about how that roller is in contact or whatever, but if you think of this as being round or something, that clearly, that roller isn't going to prevent rotation about the x-axis at all. So this is just going to produce an upward force of R.
If it did, say like it was a cylinder,
Yeah.
how would you note the torque at that point?
Yep. But what we would notice if we did that is once we got to the x moment equation, we'd have two unknowns, one equation, and so that would be statically indeterminate. Okay, so Newton's second law now says RAX, RAY plus 0 RB plus, that's 866, negative 500. This is a couple, so that doesn't go in there. And now the moment equation. Let's put the coordinate system here. And so the about point is actually going to be, if the origin's located there, let's make the about point the z-axis, you know, like right where that pin is. No. I just wanted you to still be able to see that pin, that's all. Thanks for asking. Okay, z-axis. Okay, so what moments are produced if this left end is the about point? Any moments about the z-axis produced at the left end? No. Any produced at the roller? Oh, I didn't give any. In my notes I did, but here I did not give any lengths. Let's say that's a meter, and that's a meter. Okay, so is there a moment about the z-axis produced by RB? Mm-hmm. Yeah, what's the moment arm?
1 meter.
Yeah, so 1 meter times RB, and now would that produce a clockwise or counterclockwise rotation about the end? Counter, so that's positive. And now the x component of this force wouldn't produce any moment. The y component would. So you have 500 acting down. What's the moment arm? 2. So you have 2 times 500. And a downward force of 500 there. Would that rotate it clockwise or counterclockwise? Clockwise. So that's negative. Because that is the y component of the force. That's just getting that 1,000 into components. Yeah. So yeah, the components are going to be 866x negative 500y. And of course, if you ever get confused on any of this stuff, you can always use the pancake table and just go through the calculations with the components. Do it with the cross product. So that's equal to 0. Oh, shit. Damn it. I forgot the quiz. I have them. Too late now. Nope.
I was going to say something, but I figured you knew. It's a really short quiz.
No. Okay, so this says that RB is equal to 1,000. And then that says that we can use that to say that RA is equal to negative 866, negative 500. And now we have one more to do, the moment equation about the x-axis. So what produces moments about the x-axis? TA. And then negative 500. So TA is equal to 500. So let me just draw out a free body diagram of the whole thing, and then on Friday we can start with cuts.
Did we say there wasn't a moment at the pin?
There was not an X moment at the pin, right? There's no moment at the pin. If there was a moment at the pin, and it's, at the pin? Yeah, the pin, that's the TA.
Okay, no, I was talking about.
Oh, okay. There's no Z moment because with that pin there, this thing's still free to rotate that way.
Oh, okay.
Okay, so those reactions only exist when they restrict motion. If the motion can happen with the joint there, then it doesn't produce the associated load. Okay, so final free body diagram. So we have a torque TA of 500. A force of negative 866, negative 500. What's RB? 1,000. A force from the roller of 1,000. And then the external load that was provided, that and also the applied external torque of 500. So this is Newton meters, newtons, newtons, Newton meters, newtons. Okay, so the last question before we go. How many candidates are there? It's a two-part question. How many candidates are there for boundaries for this piecewise function? Endpoint, endpoint, nice. I'm out of here. Yeah, so n equals 3. And so we're going to have to do two cuts. One for x values representing between these two, and one where x values represent between these two. We'll do that next time. Okay.